All right, so let's do the Windows version. We're going to exploit this thing called vulnerable server on Windows. And there are several adjustments you have to make on your Windows machine that I've already made. If you're using a server version of Windows, you have to turn off data execution prevention, which is the thing that prevents executing code on the stack. On client versions of Windows, it's already turned off because so much software is written, old software, that this defense will break. And typically on a client version, people want to play old games and stuff. On a server version, Microsoft expects you to buy newer versions of programs. So the default is the other way. But this is the lower setting where it's only going to be turned on for essential Windows programs and services. Then you turn off the firewall. And then just for this project, it's nice to enable error reporting. By default, modern versions of Windows do not show you the error when programs crash. And we would like to see that. So then you just have to download and run this program called Vuln Server. And let me just close some of these unnecessary things. All right. And so I've done that on this Windows machine. I've downloaded and unzipped Vuln Server. And Vuln Server is two pieces, essfunc.dil, which is some library functions that come with it, and the actual server itself. It's also open source, and in some of these projects, I've actually modified it. Anyway, this is now waiting for client connections. It's listening, and so you can communicate with it from any other machine. And in my case, I'm going to communicate with it directly from my Mac. My host machine is a Mac, and that'll be fine. And so I should have a ping. All right, I've got the address here, ping. So that server is the Windows Server 192.168.11.30. And as you see, I can reach it with a ping, so the firewall is down, and that's good. Now I can also connect to it, to the Vuln Server. The Vuln Server is listening on that address on port 9999. And see, welcome to Vulnerable Server. Enter help for help, and you'll see there are a variety of things you can have here. And this is, I think, intended to look sort of like an email server. It's just a series of nonsense words that take parameters, and it has many interesting vulnerabilities. And what we're going to do here is exploit the simplest one, which is the classical stack buffer overflow vulnerability in the trun command. And so I'll exit for now. The only point of that was to make sure that the network connection was working and you could reach it. All right. So now we're going to fuzz that server. So let's cat vs.fuzz. All right. So see, it's got the right address for the server. And this is Python 2 code. I haven't updated it yet, but I can run it in Python 2. So what this does is it asks for a length of the attack from the user, and then it sends that many capital A's. And it's trun space dot followed by the A's. That's the correct format to see it. So you can just send a certain number of A's. So if I run that, Python 2 fuzz, this is how you find vulnerabilities typically. So I can send, say, 10 A's, and then it works, doesn't crash or anything. So I can send 1,000 A's, and it works and says goodbye, nothing bad happens. And I can send 2,000 A's, and then it doesn't reply, it crashes. And on here you see it has stopped working. And so it can't handle 2,000. There is some kind of error caused by sending 2,000. So now we've discovered a denial of service attack. And the whole point of exploit development is to take a weak attack like that and try to upgrade it to a remote code execution attack. And we need a debugger, just like we did in Linux. So we'll use Immunity Debugger, which is a good modern debugger. And in the debugger, restart the program, Vuln Server. It loads the server, and it shows you the assembly code. It shows you the registers like ESP and EBP that we've used before. It shows you the stack down here, already visible. And it has a pane here where you can dump any data region you like and see it in hexadecimal and ASCII. Right now, the program is paused. When you first load a program, it loads it and pauses, assuming that you might want to examine it or perhaps modify it. I just want to run it. So I hit this button, and now it's running. Now it's listening. So now I'll send that attack again, 2000 days. And it crashed. And when it crashed at the bottom, it tells me what happened. Access violation when writing to 41414141. So it crashed because it tried to write to a memory location that was not allocated for the use of this program. And that location was 41414141. So this is a write that appears to be under my control, because those A's are some of those 2000 A's I sent ended up in the some register that was used to perform a write operation. And as we saw with the format string vulnerability, you can take over the machine with a write operation. However, it's easier to take over the machine if you can get direct control of the instruction pointer. And in this case, we can. So I'll do debug, restart to reload the program, and then run it again. So it's ready. And now I'm just going to send not 2000 days, but 3000 days. And it crashes, but this time an access violation when executing 41414141. So this is why I mentioned before, you always want to, once you find an exploit you like, you want to always send exactly the same length of data to make sure you're hitting the same exploit, because it's entirely possible that you have two different lengths that would hit different lines of code and crash in different ways. And once you've found one that you want to work with, you want to make sure you're always hitting the same vulnerability, or you will be getting confused. So I'm going to use a total length of 3000, and somewhere in that mess, I'm going to find the instruction pointer. So that's VSEIP0. Let's get out of here and take a look at that. Cat. All right. So here, there are Metasploit functions to create non-repeating patterns of characters, but I just made my own. I have I, J, and K, a triple loop and then it builds the characters. So if you run this is what it creates. It's 000A, 001A, 002A, all the way up to 499A. So it is 500 groups of 4 characters. That's a total of 2000. So I have 2000 characters worth of non-repeating stuff. And now I just need to put in VSEIP1. Now I'm going to nano it because it's going to have the wrong address in it. All right, and the address needs to be this here. All right. There. And so I put in 1000 A's. I'm assuming that it wasn't the first 1000 A's that crashed it, because remember, 1000 didn't crash it at all. It was 2000 before it crashed. So I imagine the first 1000 A's are processed correctly. And after that, I just put in the 2000 characters of non-repeating stuff, and that's the attack. And then I send to the server trun dot plus that attack plus carriage return line feed. So that's VSEIP1. Save that. And the server is crashed again, so I have to do debug, restart. Yes. And that loads it fresh, but it's not running. I have to run it. Here, now it's listening. Now I can send that Python VSEIP1. All right. And there it goes. It stopped. And I've seen this before, that crazy window. Okay, that window at the bottom that would show me why it crashed, it quit work, it vanished. And so I have to view the log window. Sometimes it does that. Instead of showing you the area you need at the bottom, it vanishes. But there it is, access violation when executing 35324131. Now, if you look at an ASCII table, let me just bring one up. This is pretty easy. I've got the important stuff memorized, but in case you don't, you find an ASCII table and you'll see a capital A is 41 in hex, and then it's 4243 for B, C, and so on. And the numbers are even easier. 0 is 30, 1 is 31, 2 is 32. So letters and numbers are pretty easy to read in raw hexadecimal. So this is the decimal 5, 2, that's the A, and 1. The only other trick, which I mentioned before, is because Intel is little endian, the string is out of order. So this is actually 1A25. And so if you go to the instructions, okay. There's the 1A25, and there it is in the middle. It's 251A, 252. That's where you find the string 1A25. So it's about halfway through. And if you count it up carefully, it's 1,006 bytes. So now I know where to put the 4 bytes to control the instruction pointer, and that's in VSEIP2. So let's do this and this. All right, and the only thing I have to do is replace this IP address with the correct IP address of that Windows server. There it is. And let's take another look at that just so I can see how it works. So it's here it is. Now it has 2006 A's, then it puts B, C, D, E, and then it puts enough F's to reach a total of 3,000. So the idea is from this calculation, I figured there was 2006, and the next 4 letters control the instruction pointer. And after that, I just pad it because the total length has to be 3,000 or I'll hit the wrong crash. So that's all it is. So let's send that one. First, I'm going to have to restart the server. Let's go back to the CPU window, which is the default. And then debug, restart. Yes. And that loads it. And now I hit run to run it. And it's running. Okay, now I can send VSEIP2. And it crashes. And now at the bottom, I see access violation when executing 45, 44, 43, 42. And that is BCDE. So I have managed to hit exactly which bytes control the EIP. All right. Now I would like to see what location is pointed to by ESP. You see ESP up here points to ASCII FFFF, which is pretty interesting. So apparently, at the point of the crash, the stack pointer points to some other characters I control, which is very nice. So right click, left click on that to highlight it, right click, and follow in dump. So down here, this is where the ESP points to at the point location of the crash, some of the F's. And if I just go up one line, you'll see it's pointing to the very first F. So the BCDE are going to end up in the instruction pointer, and then the ESP is right here. This is how we're going to overcome address space layout randomization, which we did not turn off. In fact, I don't even think you can turn it off for modern versions of Windows. So we don't know where this stuff is in memory. Every time the program runs, it'll relocate to a random location in memory. But we don't need to know because the ESP points to something we injected. So if we can just jump to the ESP, we can jump to our injected code regardless of how it's been laid out in memory. So that's good to know. Now we got to deal with bad characters. That's VS bad characters 1. So I'll debug, restart, and run again. And go back to here and take a look at bad characters. All right. Maybe it's bad characters. Nope. Okay, let's see what it is. Looks like I don't have that one to do live, but I think I'll just skip over it. It's not that important. The point is it sends all the characters from 0 to 255, and it turns out that they're all okay. You can find them all injected on the server. You have to get past the null character. And once you only include from 1 to 256, then when you examine on the server, you will see them all, 0, 1, 11, 21, F1, up to FF. So the only bad character is the null byte, which terminates strings. Okay, now, so if we could figure out how to find a jump ESP and execute it, then we would be able to run code we injected where the Fs are. And to do that, we're going to use Mona. I think I've already got Mona on here. I do. Good. So the first thing that's how to install is Mona modules. Okay, Mona is a plugin. You can write plugins for Unity, and it makes it much more powerful. And Mona is one designed just for reverse engineering. And what Mona does is it tells you about the loaded modules in memory and what defenses they have. This is address space layout randomization, which is the one that worries me. And you see that there are two modules which are not randomized in memory. One is, in fact, Vuln server, and the other is ESS func. Now, I'm trying to find a jump to ESP in one of these modules. And I might try looking in Vuln server, but the problem is Vuln server loads at this address, which is the default for any executable program in Windows, 400,000 with 2 zeros before it. So I cannot refer to any addresses containing null bytes. The null bytes will terminate the string. So even though this is not randomized, I can't insert those addresses in my code. However, the DIL, ESSfunc.dil here, does in fact load at 625,000 up to here. So there's plenty of addresses there that don't contain null bytes. So I would like to find a jump ESP in there. And that will not move. And I can then use that as my address to jump to. So that's the information. And so here's how you find jump ESP. This is Mona that will find a jump to ESP in the ESSfunc.dil program. And it's not letting me paste somehow. Let's try this one. Oh, okay. Didn't copy again. This seems to happen. I notice when I copy from a browser, it tends not to actually copy. See if it got it now. Nope. Okay. I'll just type it in. The only other way to get it is going to be opening a browser inside there. Oh, it's probably, oh, that's right. This is a cloud machine, so I don't have a connection to the clipboard. Mona jump -r ESP -m ESSfunc.dil. Looks right. And Mona command started. Okay, good. And I think it finished, but for some reason the log window didn't stay on top. And found a total of, there we are. These are the jump ESPs. It found 9 jump ESPs in there. Here you see them, jump ESP at these addresses. So there are 9 addresses, and might as well use the first one. They're all the same. If I redirect execution to this address, it will perform a jump ESP and then go to part of the data I control with my overflow. So now I have that. And now the next thing to try is to check at code execution. That's what VSEIP, remember we did this before. Before putting on real shellcode, we put in shellcode just to see if we're going to be able to execute code on the stack, because sometimes you can't. So nano VSEIP3. All right, let me get the IP address and fix it. All right. And so this is that address, 6250.11AF, that goes to jump ESP. That's what goes here. And that's going to jump to the code right after it. So I'm going to put in 16 nops and then a break. So that's like before, a nop sled, which will be nothing, 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 and then a break, which will jump back to the debugger. So let's see if it works. That's VSEIP3. Let's go back to the CPU window. And it is running, so it's ready for an attack. So let's send it VSEIP3. Not Nino, but Python. Okay, there. So there it goes, and this is good. It hit an int3 command. That's what I expected. And so, thought I would see it right there. And I do, just scroll up. There, you can see this is the instruction pointer. So it worked. Here's the here's the 625011AF. Here's the NOPS. It executed the NOPS and it executed the break and ended up here. So I now know I can get here and I can execute code I put there. So all I have to do is find fun code to put there. And again, I can do that with Metasploit. So now you can do it again with MSF Venom. You can use to create reverse TCP shell, which will phone home. And so I'm going to have to make another one here. And for that, I think I'll need my Linux machine. I don't think I have Metasploit on my Mac. So let me go to my terminal and open another terminal. Okay. And connect to my Linux virtual machine. All right. And I think I have MSF Venom on here. I do. Good. Because I'm going to have to generate new shell code because I have a different IP address. So here's the command that generates the shell code that's going to phone home on port 443 to my listening command and control server. And as in all other forms of malware, including real malware you'll find, it has to have the command and control IP address embedded in it somewhere. And here it is. And I get it from here. Okay, there's the IP address of my command and control server, which actually is wrong because I'm going to have to use this Linux machine as the command and control server. Let me do ifconfig. It's Linux. IPA. All right. 172.16. Right. Okay. I'm going to have to exit and change my networking. All right. There's always something. I got to change the networking mode of my Linux server into bridged to get it on the same network as my local cloud machine. This is the kind of thing that always happens. So here's my, I can make this to move. All right. Here's my Linux box. So I have to go to network. And I have to change it to bridged. Yep, bridged to, I think the USB will do. We'll try it and see. All right, now a password. Okay, now it's 192.168.11.9. And that looks like it's on the right network. Okay, let's see if I can connect 192.168.11.9. Really? Well, oh, that was it's not, okay. I think I have to go in here and do IPA. It is still 172. How rude. Sudo DH client -V. There, now it's 192.168.11.21. Okay. So I should be able to connect here with 21. There we go. All right. Now I can use this as the command and control server. So I copy this and it's 11.21. So 192.168.11.21. Okay, so there is the shellcode that will phone back home to my server. Now, I need to put that in VS shell. All right, so let's get here. All right, and I'm going to take VS shell and copy the old one. I got to get my VS shell. All right. I think I'll use 2 for this one. I got to have nano though. I keep hitting the wrong keys. Okay. And now I take this buffer and copy it, and I put it in instead of this stuff. And get rid of this old stuff. That should be the buffer that points to my Linux machine. And I have to put the IP address of the Windows server up here. There, that might work. So that should open a reverse shell that will phone home to this Linux server, and I need to start a listener. So it's sudo msf console. I need to run it as root because I'm going to listen on port 443, which is a privileged port. Okay, there we are. So it's use multi-handler. All right, and I can do set payload, all this stuff. I should be able to copy and paste into this SSH shell. Yep, good. And then exploit. There it's listening on 443. All right, let's get my server ready. It's paused. I need to debug, restart. Yes. And run. And now I need to send that attack. And that's Python 2. All right. So it sends that to the server. See, the server is doing things. And here it is opening the shell. So it's now given me remote control of that Windows server at my command and control server. And I can do help, see the interpreter options. And I can do things like get PID. I can do ipconfig. Should be able to get something about the operating system like sysinfo or something like that. There's the file system, networking, system commands, sysinfo. Let's try that. All right, so that's my machine, and I'm on a Windows machine. Now, if I wanted to steal the password hashes, I would have to get system privileges, and I might not be able to. Let's see if that works. Get system. We'll try a variety of standard exploits to get system, and it looks like it failed. Yep, so none of them worked. So if I try to do hash dump, it's not going to work. Yep, can't get them because I can't get system. That's not too surprising, but I do have a unprivileged shell on that machine. And that's what I wanted to show you. That's all the steps to make a real exploit to take over Windows machine.